Hey there, night wanderers and curious minds. Welcome back to Sleepy Science, where we explore the mysteries that keep you awake and eventually help you sleep. What if I told you that the chair you're sitting on right now isn't really solid, that the atoms making up your body are mostly empty space, vibrating with energy that shouldn't exist? That reality itself, at its most fundamental level, operates on rules so bizarre that even Einstein refused to accept them. On October 24th, 1927, in a hotel in Brussels, the greatest minds in physics gathered for a conference that would shatter everything we thought we knew about existence. And by the end of that meeting, reality itself had cracked wide open. If you're ready to question everything you think you know about the universe, go ahead and hit that like button. And subscribe, because over the next hour and 45 minutes, we're diving deep into 8 quantum rules that literally break reality as we know it. Trust me, you'll want to stay for all of this. So, let's rewind to that autumn day in 1927, the 5th Solvay Conference. Picture this: 29 of the most brilliant physicists ever to live, crammed into one room. We're talking about Einstein, Niels Bohr, Marie Curie, Erwin Schrödinger, Werner Heisenberg. Combined, these minds would eventually earn 17 Nobel Prizes. The topic? Electrons and photons. Sounds dry, right? But what happened in that room was nothing short of revolutionary warfare over the nature of reality itself. Einstein walked into that conference with absolute confidence in his worldview. He believed in a deterministic universe where cause and effect reign supreme, where God, as he famously said, does not play dice with the universe. He believed that if you knew all the initial conditions of a system, you could predict its future with perfect accuracy. The universe was like a cosmic clock, wound up at the Big Bang, ticking forward with mathematical precision. But there was a problem, a massive problem that had been building for nearly 3 decades. You see, starting around 1900, physicists kept stumbling over experimental results that made absolutely no sense within classical physics. Max Planck discovered that energy comes in discrete packets, which he called quanta. Einstein himself, in 1905, explained the photoelectric effect by proposing that light, which everyone thought was purely a wave, also behaves like a particle. Then, in 1913, Niels Bohr created his model of the atom, where electrons orbit in fixed energy levels, jumping between them instantaneously like a teleporting phantom. Each discovery was more disturbing than the last. And by 1927, a complete theory had emerged: quantum mechanics, a mathematical framework that predicted experimental results with stunning accuracy. There was just one problem: it was absolutely insane. According to this new quantum mechanics, particles don't have definite positions until you measure them. An electron doesn't travel from point A to point B along a specific path. It exists in all possible positions simultaneously until the moment you look. Cause and effect? Gone. Replaced by probability clouds and wave functions. The universe wasn't a clock after all. It was more like a cosmic roll of the dice. Einstein hated this, passionately. At the conference, the debates between Einstein and Bohr became legendary. They would start at breakfast and continue through dinner, walking the streets of Brussels, arguing about the very fabric of existence. Einstein would devise clever thought experiments designed to prove quantum mechanics was incomplete, that there had to be hidden variables we weren't seeing, and each morning, Bohr would show up with a refutation, demonstrating that, no, the universe really is that strange. One night during the conference, Einstein posed what he thought was the ultimate challenge. He imagined a box containing a single photon, a particle of light. The box has a shutter controlled by a clock. At a precise moment, the shutter opens briefly, allowing the photon to escape. By weighing the box before and after, and knowing exactly when the photon left. Wouldn't you know both its energy and the exact time it departed, violating Heisenberg's uncertainty principle? Einstein went to bed that night, confident he'd finally cornered Bohr. But the next morning, Bohr arrived with a devastating counter-argument, and here's where it gets beautiful in its irony. Bohr used Einstein's own general theory of relativity against him. He pointed out that the act of weighing the box in a gravitational field would create an uncertainty in time measurement, perfectly preserving Heisenberg's principle. Einstein had been defeated by his own theory. The look on his face, witnesses said, was one of genuine shock. Now, why am I spending so much time on this conference? Because this moment represents something profound. The night when humanity realized that reality, at its deepest level, is fundamentally different from everything our senses tell us. Think about your own experience right now. You feel solid. The device you're watching this on feels real and tangible. The world seems stable, predictable. Objects have definite positions. The past is fixed, the future is open, but determined by present actions. This is the classical reality that Einstein fought to preserve. But quantum mechanics says this is all an illusion, a very convincing illusion that emerges only at our macroscopic scale. Go small enough, down to atoms and subatomic particles, and reality becomes a shimmering probability field where particles exist in multiple states simultaneously, where the future can influence the past, where two particles can be instantly connected across the entire universe, where things can tunnel through barriers that should be impenetrable. And here's what keeps me up at night, and what should intrigue you. We still don't fully understand why. We have the mathematics. The equations work. Quantum mechanics is the most accurately tested theory in all of science. GPS satellites, computer chips, MRI machines, the screen you're watching this on, all depend on quantum mechanics being correct. We can use it, predict with it, build technology from it, but we can't truly explain it. We don't know what it means. After the 1927 conference, Einstein never accepted quantum mechanics as complete. Until his death in 1955, he continued to believe there was a deeper, deterministic reality hiding beneath the quantum weirdness. God does not play dice, he insisted, to which Bohr reportedly replied, "Stop telling God what to do." So, who was right? Well, that's what we are going to explore together. Because in the decades since that conference, experiment after experiment has confirmed the quantum picture. Reality really is that strange. And not only that, it's stranger than even Bohr imagined. Over the next hour and a half, I'm going to walk you through 8 specific quantum rules that break our intuitive understanding of reality. We'll look at superposition, the rule that says particles can be in multiple places at once. We'll explore entanglement, the phenomenon Einstein called spooky action at a distance. We'll dive into wave-particle duality, quantum tunneling, Heisenberg's uncertainty principle, quantum decoherence, quantum field theory, and finally, what all of this means for your understanding of consciousness and existence itself. Each of these isn't just abstract physics. Each one has been experimentally verified, sometimes in ways that shocked even the physicists doing the experiments, and each one reveals something profound about the nature of reality that contradicts everything your daily experience tells you is true. But here's what I find most fascinating, and here's why this matters for you personally. If reality at its most fundamental level is based on probability rather than certainty, on connection rather than separation, on possibility rather than fixed outcomes, what does that mean for how you live your life? The deterministic universe Einstein believed in was, in many ways, a prison. Your future was already written in the initial conditions of the Big Bang. Free will was an illusion. Everything was predetermined, just waiting to unfold. But the quantum universe? It's radically different. It's fundamentally uncertain, probabilistic, open. The future isn't written yet because reality itself is still deciding. Now, before you think I'm about to dive into pseudoscience or quantum mysticism, let me be clear, I'm not. The quantum effects we're going to discuss operate at incredibly small scales. You can't use quantum mechanics to wish your way to wealth or manifest your dreams. That's not how any of this works, but what you can do is update your mental model of what reality fundamentally is. And that shift in perspective, that can be genuinely transformative. Because if the universe at its core is uncertain, interconnected, and probabilistic, maybe rigidity in your thinking isn't serving you. Maybe the boundaries you perceive between yourself and others aren't as solid as they seem. Maybe the future is more open than you've allowed yourself to believe. That night in Brussels in 1927, when Einstein and Bohr walked the streets debating the nature of existence, they weren't just arguing about physics equations. They were arguing about what it means to be human in a universe that might be fundamentally uncertain. They were arguing about whether reality has inherent meaning or whether we, as conscious observers, play a role in creating it. And we're still having that argument today, except now we have nearly a century of experimental evidence on one side of the debate. So here's my question for you, and think about this as we move forward. What would it mean for your life if reality is fundamentally uncertain, not chaotic, but genuinely open? Where the wave function of your future hasn't collapsed yet, the quantum rules we're about to explore aren't just interesting physics. They're an invitation to see reality from a completely different perspective. A perspective that the greatest minds of the 20th century fought over, lost sleep over, and ultimately had to accept, no matter how uncomfortable it made them. Einstein spent the last 30 years of his life trying to prove quantum mechanics wrong or incomplete. He failed, not because he wasn't brilliant enough, but because reality itself refused to conform to his intuitions about how it should work. And that's where our journey really begins. Because if Einstein's intuitions about reality were wrong, what else might we be wrong about? Let's find out. Because the first quantum rule we need to understand is perhaps the strangest of all. It's the rule that says particles, and possibly everything in the universe, can exist in multiple states simultaneously until the moment you observe them. It's called superposition, and it's going to fundamentally challenge everything you think you know about what it means for something to exist. But to understand superposition properly, we need to go back even further than 1927. We need to go back to 1801, to a darkened room in England where a man named Thomas Young was about to perform an experiment that would haunt physics for the next 2 centuries. Picture a coin spinning in the air. While it's spinning, is it heads or tails? Your instinct says it's one or the other. We just don't know which yet. But quantum mechanics says something far more disturbing. While that coin is in the air, it's both heads and tails simultaneously. Not either or, but both and. And the moment it lands, the moment you look, reality makes a choice. This isn't philosophy. This isn't a metaphor. This is superposition. And in 1801, a physicist proved it in a way that still makes scientists uncomfortable today. If that just broke your brain a little bit, you're in good company. Go ahead and smash that like button because we're about to go deeper into the rabbit hole. And make sure you're subscribed because understanding superposition is the key to everything else we're going to explore. Thomas Young was a British polymath, a physician, a linguist who helped decipher Egyptian hieroglyphics, and in his spare time, apparently, someone who enjoyed completely overturning our understanding of light. In 1801, he designed what seems like an absurdly simple experiment. He took a light source, placed a barrier with 2 narrow slits in front of it, and observed the pattern that emerged on a screen behind the slits. Now, if light were made of particles, like Newton believed, you'd expect to see two bright bands on the screen, one directly behind each slit. Like throwing tennis balls at a wall with two openings, you'd get two piles of balls on the other side. Simple, right? But that's not what Young saw. Instead, he observed an interference pattern, multiple bands of light and dark alternating across the screen. This pattern could only be explained if light were a wave. When waves pass through two slits, they spread out and overlap, creating regions where they amplify each other, bright bands, and regions where they cancel each other out, dark bands. It's the same pattern you'd see if you dropped two pebbles in a pond and watched the ripples intersect. Young's experiment seemed to definitively prove that light is a wave, not a particle. Case closed. Newton was wrong. Except, here's where things get weird, and I mean really weird. Fast forward to 1905. Einstein wins his Nobel Prize not for relativity, but for explaining the photoelectric effect, a phenomenon where light knocks electrons out of metal. The only way to explain this effect was to treat light as particles, as discrete packets of energy. Einstein called them photons. So now we had a problem. Young's double-slit experiment proved light is a wave. The photoelectric effect proved light is a particle. Which is it? The answer quantum mechanics gives us is disturbing. It's both. Light is simultaneously a wave and a particle, depending on how you measure it. This is wave-particle duality, and we'll explore it more deeply later. But for now, I want to focus on what happens when we perform Young's double-slit experiment with individual particles. In the 1920s, as quantum mechanics was being developed, physicists began to wonder, what if we sent particles through the double slits one at a time? If we fire a single electron at the barrier with two slits, it has to go through one slit or the other, right? It can't go through both. Except, that's exactly what happens. In 1961, Klaus Janssen performed the double-slit experiment with electrons for the first time. He sent electrons through the apparatus one at a time. Each electron hit the detector screen as a single point, like a particle. But here's where reality starts to unravel. As you accumulate thousands of these single electron impacts, an interference pattern emerges. The same wave-like interference pattern Young saw with light. Let me emphasize what this means. Each electron goes through the apparatus individually. There's nothing to interfere with. Yet somehow, each single electron creates an interference pattern with itself. The only explanation is that each electron must somehow be going through both slits simultaneously, interfering with itself, existing in a superposition of multiple paths at once. Your brain probably just rebelled against that. Mine still does, and I've been studying this for years. It gets worse. In the 1980s, physicists decided to get clever. They thought, okay, let's just watch which slit the electron goes through. We'll put a detector at each slit and catch the electron in the act. That'll solve the mystery. So they did. They added detectors to observe which slit each electron passes through. And the moment they added those detectors, the interference pattern vanished, completely disappeared. Instead, they got exactly what you'd expect from particles. Two bands on the screen, one behind each slit. The act of measuring which slit the electron went through collapse the superposition. By observing the electron, they forced it to choose one path. When unobserved, the electron exists in a superposition of going through both slits. When observed, it becomes localized, going through one specific slit. This is the measurement problem, and it's been driving physicists insane for nearly a century. What counts as observation? Does it require a conscious observer? Does the universe somehow know when it's being watched? Here's where people often go off the rails with quantum mysticism. They hear that observation affects reality and conclude that consciousness creates reality, that you can manifest your desires through quantum mechanics. Let me be absolutely clear. That's not what's happening here. The observation in quantum mechanics isn't about consciousness or human awareness. It's about any interaction that causes a quantum system to become entangled with its environment in a way that extracts information. When the electron interacts with the detector at the slit, that interaction creates a record, a footprint in the environment. That's what collapses the superposition, not your conscious awareness of it. But even with that clarification, superposition remains deeply strange. Before measurement, the electron genuinely doesn't have a definite position. It's not that it's in one place and we just don't know where. It's that it exists in multiple places simultaneously, described by a wave function that gives probabilities for where it might be found if measured. In 1935, Erwin Schrödinger, one of the founders of quantum mechanics, became so frustrated with this interpretation that he devised a thought experiment to show how absurd it all seemed. You've probably heard of it, Schrödinger's cat. Here's the setup. You put a cat in a sealed box with a vial of poison, a radioactive atom, and a detector. If the atom decays, the detector triggers, breaks the vial, and kills the cat. If the atom doesn't decay, the cat lives. According to quantum mechanics, until you open the box and observe the system, the atom exists in a superposition of decayed and not decayed states. And if the atom is in a superposition, then the entire chain of events it triggers must also be in superposition. Which means, according to quantum mechanics, the cat is simultaneously alive and dead until you open the box and observe it. Schrödinger proposed this thought experiment to show how ridiculous quantum mechanics seemed when applied to everyday objects. He didn't think cats could actually be in superposition. He was trying to point out what he saw as an absurdity in the theory. But here's the thing, and this is what kept me awake for weeks when I first understood it. Quantum mechanics doesn't care about Schrödinger's intentions. The math says that yes, in principle, the cat is in a superposition of alive and dead states until observed. The reason we never see this in practice has to do with something called decoherence, which we'll explore in depth later. But the fundamental principle holds. Superposition isn't just for tiny particles. It's a feature of reality itself. Now, you might be thinking, this is all very theoretical. Does superposition actually matter for anything practical? Oh, it matters enormously. Every modern computer chip relies on quantum mechanics, specifically on electrons existing in superposition states within the semiconductor materials. The transistors that make up your processor work because electrons can tunnel through barriers and exist in superposition states that allow the flow of current to be controlled with incredible precision. But we're about to push this much further. Quantum computers, which are being developed right now by companies like IBM, Google, and D-Wave, explicitly harness superposition. A classical computer bit is either 0 or 1. A quantum bit, or qubit, can be in a superposition of both 0 and 1 simultaneously. 2 qubits can be in a superposition of 4 states, 0, 1, 10, and 11 all at once. 3 qubits can represent 8 states simultaneously. The number of simultaneous states grows exponentially. In October 2019, Google announced they had achieved quantum supremacy. Their quantum computer performed a specific calculation in 200 seconds that would take the world's most powerful classical supercomputer 10,000 years. How? By using 53 qubits in superposition, existing in all possible states simultaneously, essentially performing trillions of calculations in parallel. This isn't science fiction, this is happening right now, and it's possible only because superposition is real. But let me share with you the experiment that genuinely made my jaw drop, the one that showed just how far we can push superposition. In 2019, a team of physicists at the University of Vienna and MIT managed to put a molecule containing 2,000 atoms into a state of superposition. They created an interference pattern with something you could almost see with a microscope. 2,000 atoms existing in two places at once. That molecule was simultaneously traveling along two different paths, separated by a measurable distance, interfering with itself. Where do we draw the line? At what point does superposition stop and classical reality begin? We don't know. That's the honest answer. We can create superposition with increasingly large objects, but we don't fully understand the boundary between quantum and classical. It's one of the deepest unsolved problems in physics. Here's what gets me though. Every atom in your body right now, at the quantum level, exists in superposition states. The electrons orbiting your atoms aren't in definite positions. They exist in probability clouds, simultaneously occupying a range of possible locations. The particles that make up your neurons, your DNA, the molecules enabling your thoughts right at this moment, all of them are fundamentally quantum objects operating in superposition. You are, at your most fundamental level, a quantum system. The reason you don't feel like you're in multiple places at once is because of decoherence, the incredibly rapid interaction with your environment that constantly collapses these quantum superpositions into definite classical states. But for a brief moment, at the smallest scales, superposition is constantly occurring within you. Does this mean you can be in two places at once? No. The superpositions in your body are so small and collapse so quickly that they don't add up to macroscopic quantum effects. But it does mean that at the foundation of your physical existence, there's a layer of reality that operates on rules completely different from the solid, definite world you experience. So, what's the big takeaway here? Superposition tells us that reality, before observation, exists in a state of pure possibility, not as one definite outcome that we're merely ignorant about, but as a genuine multiplicity of potential states. The wave function describing a quantum system isn't just our ignorance, it's an accurate description of a reality that hasn't yet decided what it is. Think about what that means philosophically. In a classical universe, the future is already determined by the present. Given perfect knowledge of all particles and forces, you could in principle predict everything that will happen. But in a quantum universe, the future genuinely doesn't exist yet. Reality is fundamentally indeterminate until the moment of measurement, until the moment the wave function collapses and possibility becomes actuality. This isn't just about particles in labs. This is about the nature of existence itself. Before observation, before interaction, before decoherence, reality exists as a superposition of possibilities. The universe is, at its core, probabilistic rather than deterministic. And here's the question I want you to sit with. If the universe is fundamentally indeterminate, what does that mean for your sense of agency, for your choices, for the path your life takes? We're going to return to these questions at the end. But first, we need to explore another quantum rule that's even more disturbing than superposition. Because at least with superposition, the weirdness is localized to one particle, one system. But there's a quantum phenomenon where two particles separated by any distance, even across the entire universe, remain connected in a way that Einstein called spooky action at a distance. He hated this idea so much that he spent years trying to prove it couldn't possibly be real. But in 1964, a physicist named John Bell proved Einstein wrong. And what we discovered is that reality is non-local, that separation is an illusion, that connection is woven into the fabric of the universe itself. Imagine I have two coins. I flip them both, then send one to you in New York and keep one here in California. When you flip your coin and it lands on heads, mine instantly becomes tails, no matter how far apart we are. Not because they're connected by some hidden signal, but because they were the same coin existing in two places at once. This sounds like magic. Einstein certainly thought so. He spent the last 20 years of his life trying to prove this spooky action at a distance was impossible. In 1964, a physicist proved Einstein was wrong, and what we discovered changed everything we thought we knew about separation, connection, and the very fabric of space-time. If your mind just did a backflip, perfect. That means you're paying attention. Hit that like button, because we're about to explore the most mysterious phenomenon in all of quantum mechanics. And stay subscribed, because entanglement is the foundation for technologies that are going to transform our world in the next decade. Let's go back to 1935. Einstein was deeply troubled by quantum mechanics. We talked about his debates with Bohr at the 1927 Solvay conference. But by 1935, he'd found what he thought was the ultimate proof that quantum mechanics was incomplete. Along with two colleagues, Boris Podolsky and Nathan Rosen, Einstein published a paper that became known as the EPR paradox, named after their initials. Here's what bothered Einstein. According to quantum mechanics, a particle doesn't have definite properties until you measure it. An electron doesn't have a definite spin until you measure its spin. It exists in a superposition of all possible spin states. But quantum mechanics also predicts something even stranger. You can create two particles in such a way that their properties are correlated, entangled. Imagine you create two electrons from a single source in such a way that their total spin must be zero. One electron must be spin up, the other spin down. But until you measure them, neither has a definite spin. They exist in a superposition of both possibilities. Now you send these electrons in opposite directions, billions of miles apart. According to quantum mechanics, the moment you measure the spin of one electron and find it spin up, the other electron's wave function instantly collapses and becomes spin down. Instantly, not at the speed of light, instantaneously, no matter how far apart they are. Einstein found this absurd. His special theory of relativity, published in 1905, was built on the principle that nothing can travel faster than light, including information. If measuring one particle instantly affects another particle light years away, that would violate relativity. It would allow faster than light communication, which would break causality itself. So Einstein proposed an alternative explanation. He suggested there must be hidden variables, properties that the particles possess all along, even before measurement. Maybe when the two electrons are created, one is secretly spin up, and the other is secretly spin down from the very beginning. We just don't know which is which until we measure them, like having two envelopes, one containing a red ball and one containing a blue ball. You don't know which envelope has which color until you open them, but the colors were determined from the start. This made so much more sense. It preserved locality, the principle that distant objects can't instantly affect each other. It preserved realism, the idea that properties exist independently of measurement. And it meant quantum mechanics, while useful, was incomplete. There was a deeper layer of reality with hidden variables that would eventually be discovered. Einstein was certain he was right. Bohr and the quantum mechanics camp were equally certain Einstein was wrong, but it seemed impossible to settle the debate experimentally. How could you prove whether particles have hidden properties or genuinely exist in superposition? Then, in 1964, an Irish physicist named John Bell, working at CERN, published a theorem that would eventually earn him consideration for a Nobel Prize, though tragically, he died just before it could be awarded. Bell's theorem was a stroke of genius. He showed mathematically that if hidden variables exist, if particles have definite properties before measurement, then there are statistical limits on how correlated the measurements of entangled particles can be. Bell calculated specific inequalities. If hidden variables exist, the correlation between measurements must be less than a certain value. But if quantum mechanics is right, If particles genuinely exist in superposition until measured, then the correlations can exceed Bell's limit. The universe would violate Bell's inequalities. This was testable. This was the experiment that could finally settle the debate between Einstein and Bohr, even though both men had died by then. Several physicists rushed to perform the experiment. The most famous was Alain Aspect in France in the early 1980s. Aspect's experiment was elegant and definitive. He created pairs of entangled photons and sent them to detectors in opposite directions. He measured their polarizations at different angles, collecting thousands of pairs to build up statistics. The question was simple. Do the correlations obey Bell's inequalities, suggesting hidden variables and locality? Or do they violate Bell's inequalities, confirming quantum mechanics and non-locality? The results were unambiguous. Bell's inequalities were violated, significantly violated. The correlations between entangled photons were stronger than any hidden variable theory could explain. Einstein was wrong. Quantum mechanics was right. The universe is fundamentally non-local. Let me be very precise about what this means, because it's easy to misunderstand. When you measure one entangled particle, you do instantly affect its partner, no matter the distance. But, and this is crucial, you can't use this to send information faster than light. Here's why. When you measure your entangled photon's polarization, you get a random result. Maybe it's horizontal, maybe it's vertical. You have no control over what result you get. It's genuinely random. Your partner, measuring their photon at the same time, also gets a random result. Only when you later compare your results, through classical communication at the speed of light or slower, do you discover the perfect correlation. So you can't use entanglement to send a message. You can't force your photon into a particular state to signal something to your partner. The randomness of quantum mechanics prevents faster-than-light communication, preserving causality. But the correlation itself, the connection between the particles, that's instantaneous and real. This is what Einstein called spooky action at a distance. He meant it as an insult, as evidence that quantum mechanics must be wrong. But we now know it's an accurate description of reality. The universe is spooky. Particles that have interacted remain connected in a way that transcends space and time. But the experiments didn't stop in the 1980s. We've pushed entanglement to extremes that would have shocked even the quantum mechanics pioneers. In 2017, Chinese scientists used a satellite called Metis to create entangled photons and beam them down to Earth. They successfully maintained entanglement across 1,200 kilometers, 745 miles. Two photons, separated by a distance longer than the length of California, remained instantaneously connected. Think about what this means. These photons had never been physically near each other after their initial entanglement, yet measuring one instantly determined the state of the other across 1,200 kilometers. Space at the quantum level doesn't mean what we think it means. Distance is somehow negotiable. In 2019, researchers took it even further. They entangled a ground-based quantum memory in Austria with a photon that had traveled up to a satellite and back down to a detector in China. They created entanglement between objects separated by more than 1,400 kilometers with an atmospheric layer and the vacuum of space in between. Entanglement doesn't care about barriers or distance. Now, here's where this gets truly weird and where we start touching on implications that go far beyond physics. Some interpretations of quantum mechanics suggest that entanglement might be more fundamental than space itself. There's a growing body of research suggesting that space-time, the fabric of the universe, might emerge from quantum entanglement. Physicists like Juan Maldacena and Leonard Susskind have explored the idea that the geometry of space, the distances between objects, might be determined by the pattern of entanglement between quantum fields. In this view, entanglement isn't a weird phenomenon happening in space. Space itself is a phenomenon emerging from entanglement. The universe is fundamentally a web of quantum connections, and the three-dimensional space we experience is like a shadow cast by this deeper quantum reality. This sounds like abstract theoretical physics, and it is. But it's being taken seriously by top researchers because the mathematics is compelling. And if it's true, it means that the separation you feel from other people, from distant stars, from the far edge of the universe, that separation might be an illusion created by the particular pattern of entanglement your local quantum state has access to. Now, let's talk about what entanglement is not, because there's a lot of misunderstanding out there. Entanglement does not mean you're psychically connected to other people. It doesn't mean you can send thoughts faster than light. It doesn't validate most of what gets called quantum healing or quantum consciousness. Here's why. While it's true that particles in your body can be entangled, these entanglements are incredibly fragile. The warm, wet, noisy environment of a living cell causes decoherence almost instantly. Any entanglement that forms between particles in your brain and particles in someone else's brain would collapse in femtoseconds, quadrillionths of a second, far too quickly to have any meaningful effect on thought or consciousness. But, and this is a subtle but, there are hints that biological systems might use quantum effects, including possibly entanglement, in ways we're just beginning to understand. Birds appear to use quantum entanglement in their eyes to sense Earth's magnetic field for navigation. Photosynthesis in plants operates with quantum coherence that persists longer than we thought possible. And there's speculative but intriguing research suggesting that microtubules in neurons might maintain quantum states longer than expected. I'm not claiming consciousness is quantum mechanical. We don't know. But the door is more open than it used to be. What we can say definitively is that entanglement is real. It's been experimentally verified thousands of times, and it reveals that the universe is fundamentally interconnected in ways that defy our intuitive understanding of space and separation. Let me share a personal moment with you. When I first truly understood entanglement, when I internalized that two particles can remain connected regardless of distance, I felt something shift in how I viewed existence. Not in a mystical sense, but in a profound recognition that the boundaries we perceive, the separation between self and other, between here and there, these boundaries might be more fluid than they appear. We live in a universe where connection is woven into the fabric of reality, where particles that have once interacted remain linked in a way that transcends spatial separation, where the measurements you make here can instantaneously correlate with events happening on the other side of the cosmos. Does this mean we're all one? In a rigorous scientific sense, no. Your consciousness is localized to your brain. You're not telepathically linked to everyone else. But in a deeper sense, the universe is revealing itself to be more unified, more interconnected than the separate, isolated reality our senses present to us. Here's what keeps me awake. If entanglement is real, and we know it is, what does that say about the nature of relationship? Not just between particles, but between people. We know that when you interact meaningfully with another person, particles in your brain and their brain exchange photons create correlations, become briefly entangled before decoherence destroys these connections. Is there a sense in which every deep connection you make leaves a subtle quantum footprint, a pattern of correlations that, while unobservable, is nonetheless real? I don't know. Nobody knows. But entanglement opens the door to questions about connection that go far beyond the laboratory. The practical applications are revolutionary too. Quantum cryptography, which is already being deployed, uses entanglement to create unhackable communication. If someone tries to intercept the entangled photons carrying your encrypted message, the act of measurement would destroy the entanglement, alerting you to the security breach. China has already launched a quantum communication network using satellite-based entanglement. Unhackable communication is here. Quantum computing, as I mentioned earlier, uses entanglement along with superposition to perform calculations impossible for classical computers. When qubits are entangled, measuring one gives you information about all the others instantly, allowing quantum computers to solve certain problems exponentially faster than any classical machine could. And there are proposals for quantum teleportation, which, despite the science fiction name, is real. You can't teleport matter or energy, but you can teleport quantum states using entanglement. In 2017, Chinese scientists successfully teleported a quantum state from Earth to a satellite 1,400 kilometers away. This isn't Star Trek. You're not beaming up, but you are transferring quantum information instantaneously across vast distances. So, what's the takeaway? Entanglement tells us that the universe is non-local. That separation, while real at the scale we experience, is not fundamental. That connection persists in ways that transcend space and time. That reality is woven together by invisible threads of correlation that link particles across the cosmos. And here's the philosophical question I want to leave you with. If the universe is fundamentally interconnected at the quantum level, what does that mean for how you see your place in it? Are you a separate entity navigating a disconnected universe? Or are you a localized expression of a deeply interconnected whole? We're going to keep pushing on these questions. But before we can go further, we need to address something even stranger than entanglement. We need to talk about the fact that everything we've discussed so far, particles, photons, electrons, none of them are quite what they seem. Because quantum mechanics reveals that these entities don't have a single, fixed identity. An electron isn't a particle or a wave. It's somehow both simultaneously. And the way it manifests depends entirely on how you choose to look at it. This is wave-particle duality. And it's about to challenge everything you thought you knew about the nature of matter and light itself. Hold a flashlight in your hand, the beam of light streaming out. Is it made of waves rippling through space, or particles shooting out like microscopic bullets? Your instinct might say one or the other, but quantum mechanics says something that should be impossible. It's both. Not sometimes a wave and sometimes a particle, but genuinely both at the same time. And here's what makes it truly disturbing. The way light behaves depends entirely on how you choose to observe it. It's as if reality itself is waiting for you to decide what question to ask before it commits to an answer. In 1924, a young French physicist proposed something so radical that Einstein called it a very interesting idea. By 1927, experiments proved this idea demolished our entire understanding of matter. If that just made you question whether anything is what it seems, excellent. You're thinking like a quantum physicist. Go ahead and hit that like button, because we're about to dive into the most philosophically troubling aspect of quantum mechanics. And make sure you're subscribed, because wave-particle duality is the key to understanding why reality behaves so strangely at the quantum level. Let's start with a problem that tormented physicists for centuries. What is light? Isaac Newton, in the late 1600s, was convinced light was made of particles, which he called corpuscles. He had good reasons. Light travels in straight lines, casts sharp shadows, and reflects off surfaces like bouncing balls, all particle behavior. But then, in the early 1800s, as we briefly touched on earlier, Thomas Young performed his double-slit experiment and created an interference pattern that could only be explained if light were a wave. Waves spread out, overlap, interfere. Particles don't. For over a century after Young's experiment, the scientific consensus was clear. Light is a wave, specifically an electromagnetic wave, as James Clerk Maxwell proved in the 1860s. Case closed. Except in 1900, Max Planck stumbled upon a problem. He was trying to explain why hot objects glow the way they do, what's called black-body radiation. Using classical physics, the math predicted that hot objects should emit infinite energy at high frequencies, which obviously doesn't happen. Your oven doesn't emit infinite ultraviolet radiation when you bake cookies. Planck found he could fix the equations by making a strange assumption. What if energy doesn't flow continuously but comes in discrete chunks, in quanta? He treated it as a mathematical trick, not a statement about reality. But the trick worked perfectly. Then, in 1905, Einstein went further. He was trying to explain the photoelectric effect, a phenomenon where light shining on metal knocks electrons loose. The strange thing was, dim blue light could knock electrons out, but bright red light couldn't, no matter how intense. If light were purely a wave, intensity should matter, not color. But if light came in particle-like packets, photons, each carrying energy proportional to its frequency, suddenly everything made sense. Blue photons pack more energy than red photons. One blue photon can knock an electron loose, one red photon can't. And adding more red photons doesn't help because each individual photon lacks the necessary energy. Einstein won his Nobel Prize for this work, not for relativity. And it reopened a question everyone thought was settled. Is light a particle or a wave? The answer should have been simple. Pick one. Do better experiments to figure out which one is correct. But every time physicists did a wave-type experiment, light behaved like a wave. Every time they did a particle-type experiment, light behaved like a particle. It was like trying to nail down mercury. Light's identity shifted depending on how you looked at it. Then, in 1924, a young French aristocrat named Louis de Broglie, working on his PhD thesis, proposed something audacious. If light, which everyone thought was a wave, can behave like a particle, then maybe matter, which everyone knew was made of particles, could behave like a wave. De Broglie suggested that every particle has an associated wavelength, now called the de Broglie wavelength, inversely proportional to its momentum. Massive objects moving quickly have tiny wavelengths, so small we never notice their wave nature. But electrons, being light and moving relatively slowly in atoms, should have wavelengths large enough to create observable wave phenomena. His thesis committee was skeptical. One examiner, Paul Langevin, sent the thesis to Einstein asking for his opinion. Einstein's response? He called it a very interesting idea and predicted it would be confirmed experimentally. That endorsement got de Broglie his PhD. 3 years later, in 1927, it earned him a Nobel Prize. Because in 1927, something extraordinary happened. Clinton Davison and Lester Germer at Bell Labs were studying how electrons bounce off nickel crystals. They weren't looking for wave behavior, they were doing materials research. But they noticed something strange in their data. Electrons were reflecting off the crystal at specific angles, creating a pattern that looked exactly like X-ray diffraction. Diffraction is a wave phenomenon. When waves pass through or around obstacles spaced at intervals similar to their wavelength, they create characteristic interference patterns. X-rays, being electromagnetic waves, diffract when bouncing off the regularly spaced atoms in a crystal. But electrons were particles. Particles don't diffract, except these electrons were diffracting. The pattern Davison and Germer observed could only be explained if electrons were behaving as waves, with a wavelength exactly matching de Broglie's prediction. Electrons, solid matter, the stuff that makes up atoms, were waves. Simultaneously in Britain, George Paget Thomson, Ironically, the son of J.J. Thomson, who discovered the electron as a particle in 1897, was firing electrons through thin metal films. He also observed diffraction patterns. Father discovers electron is a particle. Son proves electron is a wave. Both won Nobel Prizes. Reality apparently has a sense of humor. But here's where it gets truly weird, and this is what should keep you awake. Wave-particle duality isn't just a quirk of quantum objects. It's a statement about the nature of reality itself. In 1978, John Archibald Wheeler, one of the great physicists of the 20th century, proposed a thought experiment called the delayed choice experiment. It was designed to probe exactly when a photon decides whether to be a wave or a particle. In 2007, physicists actually performed this experiment, and the results are mind-bending. Here's the setup. You send a photon toward a beam splitter, a half-silvered mirror that reflects 50% of light and transmits 50%. If the photon is a particle, it must go one way or the other, either reflected or transmitted. If the photon is a wave, it splits, with half going each direction. After the beam splitter, the two paths recombine at another point where you can choose to place a detector. Here's the crucial part. You make the choice of whether to place that detector after the photon has already passed through the beam splitter. You decide how to measure the photon after it's already chosen its path. If you don't place the detector, you see interference, proving the photon went both paths as a wave. If you do place the detector, you catch the photon coming from only one path, proving it went one way as a particle. Your choice of measurement, made after the photon passed the beam splitter, determines whether it was a wave or particle all along. This seems to violate causality. How can a future choice affect past behavior? But the experiments confirm it happens exactly this way. The photon doesn't have a definite identity as wave or particle until the measurement is complete. Your choice of what to measure forces reality to retroactively decide what the photon was doing. Let me emphasize this because it's crucial. The photon doesn't secretly choose one path, and we're just unaware. The quantum state genuinely contains both possibilities. Only when you make a measurement that's incompatible with wave behavior does the photon become a particle. Make a measurement compatible with wave behavior, and it becomes a wave. This isn't about disturbing the photon with your measurement apparatus. This is far deeper. The type of measurement you choose determines what aspect of reality manifests. The photon has both wave and particle nature simultaneously. An observation doesn't just reveal which one it is. Observation participates in creating which one it becomes. In 1927, Niels Bohr formalized this with his principle of complementarity. Wave and particle descriptions, he said, are complementary. Both are necessary to fully describe quantum reality, but you can never observe both aspects simultaneously. The experiment you design determines which aspect manifests. Reality is complementary, not contradictory. But why? Why does reality behave this way? That's the question nobody can fully answer. We can describe it mathematically with exquisite precision. The wave function gives us probabilities for all possible measurements. But we don't have a deeper explanation for why measurement causes the wave function to collapse into one specific outcome. Here's what we do know. Wave-particle duality is universal. It's not just photons and electrons. In 1999, researchers in Vienna demonstrated wave interference with buckyballs, molecules containing 60 carbon atoms each. In 2011, they did it with molecules containing over 800 atoms. These are objects large enough to be visible under some microscopes, yet they still exhibit quantum wave behavior. Where does it end? At what point does something become too large to exhibit wave-particle duality? We don't have a fundamental answer, As objects get larger, their de Broglie wavelength gets smaller, making wave behavior harder to observe. And decoherence, the interaction with the environment, destroys quantum coherence very quickly for large objects. But there's no known size limit where quantum mechanics stops applying. Your smartphone camera relies on wave-particle duality. The sensor is made of millions of tiny detectors called photodiodes. When light hits the sensor, it behaves as particles, with individual photons knocking electrons loose in the silicon, creating the electrical signals that become your image. But the light traveled to your camera as a wave, diffracting through the lens aperture, interfering with itself. In a single photograph, light manifests both its wave nature and its particle nature. Every time you take a picture, you're capturing evidence that reality has a dual nature that transcends our classical intuitions. Let me share something that fundamentally changed how I see the world. Wave-particle duality means that identity isn't fixed. An electron isn't fundamentally a particle that sometimes acts wavy, or a wave that sometimes acts particle-like. It's both, genuinely both, and which aspect manifests depends on the context, on the question being asked. This has profound implications if you think about it. We tend to think of things, including ourselves, as having fixed identities. You are this person with these traits and these circumstances. But quantum mechanics suggests reality is more fluid. Identity is contextual, relational, dependent on how you're observed, on what questions are being asked. I'm not saying you literally exhibit wave-particle duality. You're too large, too entangled with your environment. But at the foundation of your physical being, the particles that constitute you are quantum objects without fixed identities. And perhaps there's a metaphor here. A way of thinking about identity itself as more fluid and contextual than our everyday experience suggests. Here's a question I want you to consider. In your own life, do you show up differently in different contexts? With family versus colleagues versus strangers? Is there a true you underneath all these manifestations? Or are you, like quantum objects, genuinely different depending on the context, on how you're being observed? The most common mistake people make with wave-particle duality is thinking it's about our ignorance, that the particle really is one thing and we just don't know which until we measure. But that's not it. The quantum state before measurement isn't in a state of ignorance about what it is. It genuinely exists as both, as a superposition of complementary properties. Measurement doesn't reveal a pre-existing reality. Measurement participates in creating the reality that manifests. This is uncomfortable. We want reality to be definite, to exist independently of observation. But wave-particle duality, confirmed in countless experiments over nearly a century, tells us that reality at the quantum level is fundamentally relational. What manifests depends on what questions you ask. And here's the thing that keeps me awake. If matter and energy are fundamentally contextual, their properties determined by the act of measurement, what does that say about the solidity we experience? About the definite, unchanging world our senses present to us? It says that world is an illusion, not in a mystical sense, but in a precise scientific sense. The classical world of definite objects with fixed properties is an emergent phenomenon, arising from the quantum world of waves and particles and superpositions through processes we're still trying to fully understand. You are, right now, made of quantum objects that don't have fixed identities. Particles that are simultaneously waves, waves that are simultaneously particles, existing in superpositions that collapse into definite states only through continuous interaction with their environment. The chair you're sitting on, the air you're breathing, the neurons firing in your brain, all of it is quantum at the foundation. So, what's the key takeaway? Wave-particle duality reveals that reality doesn't fit into our intuitive categories. The universe isn't made of definite things with fixed properties. It's made of processes, of potentials, of complementary aspects that manifest depending on context. Identity at the quantum level is fluid, and if the foundation of physical reality is fluid, contextual, and complementary, maybe our understanding of ourselves and our world should be more fluid too. Maybe the rigid categories we impose, the fixed identities we cling to, are in some sense fighting against the fundamental nature of existence itself. But wave-particle duality, as strange as it is, isn't the end of quantum weirdness. In fact, we're about to encounter something even more counterintuitive, because quantum mechanics predicts that particles can do something that should be absolutely impossible. They can tunnel through barriers, passing through walls that they don't have enough energy to climb over. It's as if you could walk through a brick wall simply because quantum mechanics says there's a tiny probability you might. This is quantum tunneling, and without it, the sun wouldn't shine, life wouldn't exist, and you wouldn't be watching this right now. Imagine standing in front of a solid brick wall. You don't have enough energy to climb over it, you can't break through it, yet you walk forward and somehow find yourself on the other side. Impossible, right? In our everyday world, absolutely. But at the quantum level, this happens constantly. Particles routinely pass through barriers they don't have enough energy to overcome. It's called quantum tunneling, and it's not just some laboratory curiosity. Right now, in the core of the sun, hydrogen nuclei are tunneling through electromagnetic barriers to fuse together. Without quantum tunneling, the sun would be dark, Earth would be frozen, and you wouldn't exist. In 1928, a young Russian physicist named George Gamow used this impossible phenomenon to solve one of the greatest mysteries in physics. And what he discovered changed everything. If your brain just refused to accept what I just said, perfect. That's the appropriate response. Smash that like button, because we're diving into one of the most counterintuitive and consequential phenomena in all of quantum mechanics. Stay subscribed, because by the end of this section, you'll understand why the device you're watching this on only exists because of impossible quantum behavior. Let's go back to 1896. Henri Becquerel accidentally discovered radioactivity when he left uranium salts on a photographic plate and found the plate had been exposed. 2 years later, Marie and Pierre Curie isolated radium and studied how radioactive atoms spontaneously decay, shooting out particles with enormous energy. This presented a profound mystery. Inside an atomic nucleus, protons and neutrons are held together by the strong nuclear force, one of the most powerful forces in nature. If you calculate the energy needed to escape a nucleus, it's enormous, like trying to climb out of a deep well with walls made of diamond. Yet somehow, alpha particles, which are helium nuclei, regularly escape from radioactive atoms. Where were they getting the energy? Classical physics had no answer. According to classical mechanics, if a particle doesn't have enough energy to overcome a barrier, it simply can't get through. Period. It would be like throwing a ball at a wall. If the ball doesn't have enough energy to knock down the wall, it bounces back. It doesn't magically appear on the other side. But radioactive decay was happening all around us. Atoms were shooting out particles that shouldn't have the energy to escape. For 30 years, nobody could explain it. Then, in 1928, George Gamow, working independently, and Ronald Gurney and Edward Condon, working together, applied the new quantum mechanics to the problem. And they discovered something shocking. In quantum mechanics, particles aren't localized to a single point. They're described by wave functions that extend through space with different probabilities. When a particle encounters a barrier, its wave function doesn't stop at the barrier surface. It leaks through. Inside the barrier, the wave function decays exponentially, For thick barriers or heavy particles, it decays so quickly that there is essentially zero probability of the particle appearing on the other side. But for thin barriers or light particles, there's a small but non-zero probability that the particle can be found beyond the barrier, even though it never had enough energy to climb over it. The particle doesn't dig through. It doesn't chip away at the barrier. It tunnels. One moment it's on one side, the next moment it's on the other, having traversed the barrier without ever being inside it in any classical sense. Gamow calculated the probability of alpha particles tunneling out of uranium nuclei. His predictions matched the observed decay rates perfectly. Quantum tunneling explained radioactivity. The Nobel Committee was so impressed that Gamow would likely have won the prize, except the rules at the time required experimental confirmation by the nominator, and his nominator couldn't provide it in time. But his theory was revolutionary. Now, let me show you why this matters more than you might think. Look up at the sun. Every second, the sun converts 600 million tons of hydrogen into helium through nuclear fusion, releasing the energy that warms our planet and makes life possible. But fusion requires bringing two hydrogen nuclei close enough that the strong nuclear force can bind them together. Here's the problem. Hydrogen nuclei are both positively charged and, like charges, repel strongly. The electromagnetic repulsion between two protons is enormous at close range. It's called the Coulomb barrier, and it requires temperatures of hundreds of millions of degrees to overcome through thermal energy alone. But the core of the sun is only about 15 million degrees Celsius. That's hot, incredibly hot, but it's not hot enough. At 15 million degrees, protons don't have sufficient kinetic energy to overcome the Coulomb barrier through classical physics. The sun shouldn't be shining. According to classical calculations, the sun should be dark and dead. Except it's not, and you know why. Quantum tunneling. The protons in the sun's core don't have enough energy to climb over the Coulomb barrier, but their wave functions leak through it. There's a small probability, roughly 1 in a trillion collisions, that two protons will tunnel through the electromagnetic barrier and fuse together. It sounds like terrible odds, but there are so many protons in the sun's core, colliding so frequently that fusion happens at exactly the rate we observe. Without quantum tunneling, the sun would need to be far hotter to shine. And if it were that much hotter, it would burn through its fuel much faster. Stars like our sun wouldn't live for 10 billion years. They'd live for maybe a few million. Life as we know it requires stable stars that shine steadily for billions of years. Quantum tunneling makes that possible. You exist because particles can tunnel through impossible barriers. But it gets more personal than that. The flash memory in your phone, the SSD in your laptop, every USB drive you've ever used, they all store data using quantum tunneling. Here's how. Flash memory stores information as electric charge trapped on tiny islands of conductive material called floating gates. These gates are surrounded by insulators that would normally prevent electrons from escaping. In classical physics, once you trap an electron behind a sufficient barrier, it stays trapped forever. But in quantum mechanics, electrons can tunnel through the insulating barrier. When you write data to flash memory, you apply a large voltage that increases the tunneling probability, allowing electrons to tunnel onto the floating gate. When you erase data, you reverse the voltage and electrons tunnel back off. The presence or absence of charge on the gate represents a 1 or a 0, storing your data. Every photo on your phone, every file on your computer, exists because electrons can tunnel through barriers that classical physics says are impenetrable. In 1981, Gerd Binnig and Heinrich Rohrer at IBM invented the scanning tunneling microscope, or STM, and it revolutionized our ability to see and manipulate individual atoms. They won the Nobel Prize in 1986 for this invention, and it's based entirely on quantum tunneling. Here's how it works. You bring an atomically sharp metal tip incredibly close to a surface, just a few angstroms away, a few times the diameter of an atom. You apply a voltage between the tip and the surface. In classical physics, nothing should happen. There's a vacuum gap between the tip and the surface. Electrons can't jump across a vacuum without sufficient energy, but quantum mechanically, electrons can tunnel across the gap. The tunneling current is exquisitely sensitive to distance. Move the tip just 1 angstrom closer, and the current can increase by an order of magnitude. By measuring the tunneling current as you scan the tip across the surface, you can map out the position of individual atoms. In 1989, Don Eigler at IBM used an STM to arrange 35 xenon atoms on a nickel surface to spell out IBM in letters only a few nanometers tall. He grabbed individual atoms and dragged them into position, one by one. This was the first time humans had manipulated matter at the atomic scale, and it was possible only because electrons can tunnel between the STM tip and the atoms, allowing the tip to feel where each atom is located. Today, scanning tunneling microscopes are used in laboratories worldwide to image surfaces at atomic resolution, to study chemical reactions as they happen, and to build nanostructures atom by atom. We can literally see atoms because of quantum tunneling. Now here's where things get truly strange, and this is something that doesn't get talked about enough. Quantum tunneling means that there's a non-zero probability, vanishingly small but technically not zero, that you could tunnel through a wall, or that all the air molecules in the room could simultaneously tunnel into one corner, leaving you in vacuum, or that a coffee cup could spontaneously tunnel through a table. Let me be very clear. These things will never happen. The probability is so astronomically small that you could wait longer than the age of the universe, many times over, and never see it occur. Why? Because the probability of tunneling decreases exponentially with the mass of the object and the thickness of the barrier. For anything larger than a single molecule, the probability becomes effectively zero. But effectively zero isn't exactly zero, and that's philosophically unsettling. Classical physics says these events are impossible, full stop. Quantum mechanics says they're merely extraordinarily improbable. There's a difference between will never happen and almost certainly will never happen in the lifetime of the universe. Quantum mechanics operates on the second principle. In 2001, physicists managed to observe tunneling in real time for the first time. They used ultra-fast laser pulses to watch electrons tunnel out of atoms in just a few attoseconds, billionths of a billionth of a second. What they discovered was puzzling. The tunneling seemed to be instantaneous. The electron disappeared from one side of the barrier and appeared on the other with no time spent inside the barrier. This raises a bizarre question. How fast does quantum tunneling happen? Some experiments suggest it's instantaneous, that particles spend literally zero time inside the barrier. Other experiments suggest there's a measurable traversal time. The debate is still ongoing, and it touches on fundamental questions about the nature of time itself at the quantum scale. What we do know is that tunneling can't be used to send information faster than light. Even though the particle appears on the other side of the barrier almost instantly, the process is random. You can't control when tunneling will occur for any individual particle, so you can't encode information in the timing. Causality is preserved, but just barely. Enzymes in your body rely on quantum tunneling. When an enzyme catalyzes a reaction, it often needs to move a hydrogen atom, which is just a proton, from one molecule to another. Classically, the proton would need enough thermal energy to hop over the energy barrier between the molecules. But at body temperature, there often isn't enough energy for this to happen at the rates we observe. quantum tunneling solves the problem. Protons and enzymatic reactions routinely tunnel through energy barriers, allowing reactions to proceed far faster than classical chemistry would predict. There's growing evidence that quantum effects, including tunneling, play a significant role in biological processes. Photosynthesis, enzyme catalysis, even possibly the sense of smell, may all involve quantum tunneling. Let me tell you about an experiment that truly captures the strangeness of tunneling. In 2015, researchers at the Max Planck Institute performed an experiment where they measured how long it takes for an electron to tunnel out of an atom. They used incredibly precise laser timing to measure the process. What they found shocked them. When they measured the tunneling time, they got negative values. The electron appeared to exit the atom before it entered the tunneling region. Now, this doesn't violate causality, and it's not time travel. What's happening is that the measurement of when the electron tunnels is itself a quantum phenomenon subject to uncertainty. But the fact that we can get negative tunneling times tells you just how far removed quantum behavior is from our classical intuitions. Here's what I find most fascinating about quantum tunneling. It's a direct manifestation of the probabilistic nature of quantum mechanics overriding what seems like a deterministic classical barrier. In classical physics, barriers are absolute. Can't climb over it, then you're stuck. But quantum mechanics says that barriers are probabilistic. There's always some chance, no matter how small, of getting through. This has philosophical implications if you think about it deeply. In a classical universe, obstacles are absolute. You either have the resources to overcome them, or you don't. But in the quantum universe, obstacles are probabilities. With sufficient attempts, with the right conditions, barriers can be overcome even when you shouldn't have enough energy to do so. I'm not suggesting you can tunnel through your life problems the way an electron tunnels through a barrier. Human-scale determinism still applies. But there's something profound about living in a universe where impossibility is replaced by improbability, where barriers are negotiable rather than absolute. Think about the sun again. For billions of years, every second of every day, protons in the core have been tunneling through barriers they don't have the energy to overcome. And that impossible act, repeated countless times, powers all life on Earth. The impossible, repeated enough times, becomes inevitable. Here's a question for you. What barriers in your own thinking might be more permeable than they appear? What assumptions about what's possible might be more like classical physics than quantum reality? I'm not talking about magical thinking. I'm talking about recognizing that probability isn't the same as impossibility. The mistake most people make with quantum tunneling is thinking it means anything is possible. It doesn't. The probability of macroscopic tunneling is so small that it's effectively impossible. But what tunneling does teach us is that the universe operates on probability rather than certainty, that barriers have a different character than our everyday experience suggests, that the impossible and the highly improbable are different categories. And here's the thing that keeps me awake. Every moment inside your body, quantum tunneling is happening millions of times per second. Electrons tunneling through barriers in your cell membranes, protons tunneling in enzymatic reactions. The impossible is routine at the quantum scale, even while it remains impossible at the human scale. You are, in a very real sense, a system that relies on impossible quantum phenomena to function. The energy production in your mitochondria, the chemical reactions in your neurons, the processing of nutrients in your cells, all of it involves quantum tunneling at some level. Life itself is built on quantum impossibilities. So, what's the ultimate takeaway? Quantum tunneling reveals that barriers in the quantum world are probabilistic, not absolute. That particles can achieve outcomes that classical physics forbids. that probability can overcome energy deficits, that the universe, at its foundation, operates on maybe rather than definitely not. And if the foundation of physical reality operates on probability rather than certainty, on possibility rather than impossibility, perhaps that tells us something about the nature of existence itself. Perhaps rigidity is the illusion and fluidity is the truth. But quantum tunneling isn't the only way that quantum mechanics violates our intuitions about limits and certainty. There's another principle, perhaps the most famous of all quantum rules, that tells us there's a fundamental limit to how much we can know about reality. Not a practical limit based on our measurement tools, but a limit built into the fabric of existence itself. It's called Heisenberg's uncertainty principle, and it doesn't just say we can't measure everything perfectly. It says that reality itself doesn't have perfect answers to give. Some properties simply don't exist with definite values until we measure them, and measuring one property necessarily makes another property fuzzy. This isn't about our ignorance. It's about reality being fundamentally uncertain. Try this thought experiment. You're watching a car drive down a highway. Can you know exactly where it is and exactly how fast it's going at the same instant? Common sense says yes, just measure both carefully enough. But quantum mechanics says something that should shake you to your core. No, there's a fundamental limit built into reality itself. The more precisely you know a particle's position, the less precisely you can know its momentum. And this isn't about imperfect instruments or clumsy measurements. This is about the universe having a built-in fuzziness, a cosmic blur that no technology can ever eliminate. In 1927, Werner Heisenberg discovered this principle, and it triggered one of his most famous quotes. The more precisely the position is determined, the less precisely the momentum is known, and vice versa. This wasn't a statement about our limitations. It was a statement about reality itself. If that just unsettled you, good. You're beginning to understand why Einstein found quantum mechanics so disturbing. Hit that like button, because we're about to explore the most philosophically profound principle in all of physics. And make sure you're subscribed, because the uncertainty principle is the gateway to understanding some of the strangest phenomena in the universe, including why empty space isn't actually empty. Let's set the scene. It's February 1927, just months before the famous Solvay conference. Werner Heisenberg, only 25 years old, is working with Niels Bohr in Copenhagen. They've been developing the mathematical framework of quantum mechanics, and it's been remarkably successful at predicting experimental results. But Heisenberg is troubled by something fundamental. In classical physics, you can, in principle, measure a particle's position and momentum with arbitrary precision. Give me better instruments, more careful procedures, and I can measure both to as many decimal places as I want. There's no theoretical limit, only practical ones based on technology. But Heisenberg realized something disturbing when he tried to apply this thinking to quantum mechanics. He imagined trying to measure an electron's position very precisely. To see something, you need to bounce light off it. The shorter the wavelength of light, the more precisely you can determine position, like using a finer ruler. But here's the problem. Shorter wavelength means higher frequency, and Einstein had shown that higher frequency light carries more energy in each photon. So, to measure the electron's position precisely, you hit it with a high-energy photon. But that high-energy photon kicks the electron, changing its momentum unpredictably. You've gained precision in position at the cost of precision in momentum. Conversely, if you use low-energy photons to avoid disturbing the electron's momentum, those photons have long wavelengths, and you can't determine position precisely. Heisenberg's first instinct was that this was about the disturbance caused by measurement, Like trying to check the air pressure in a tire, some air always escapes in the process. But as he worked through the mathematics, he realized something far more profound. This wasn't about the disturbance of measurement. This was about the nature of quantum states themselves. In quantum mechanics, a particle's state is described by a wave function. If you want the particle to have a very precise position, you need a wave function that's concentrated in a tiny region of space, a sharp peak. But mathematically, to construct such a sharp peak, you need to add together waves of many different wavelengths. And wavelength is related to momentum. So a sharp position means the wave function contains many different momentum components. The particle doesn't have a definite momentum. Conversely, if you want a definite momentum, you need a wave function with a single wavelength, a pure sine wave. But a pure sine wave extends throughout all space. The particle doesn't have a definite position. This wasn't about measurement disturbing things. This was about the quantum state itself. A particle cannot simultaneously have both a definite position and a definite momentum. It's not that we don't know both values. It's that both values don't exist simultaneously. Heisenberg formalized this in his famous uncertainty principle. The product of the uncertainty in position and the uncertainty in momentum must be greater than or equal to Planck's constant divided by 4p. Mathematically, dikit sox dp or yasho so saidash 2. Where is the reduced Planck constant? This is a fundamental limit, not a practical one. No technology, no matter how advanced, can violate this principle. It's woven into the fabric of quantum reality. But position and momentum aren't the only pair of properties linked by uncertainty. There's another pairing that's even more profound: energy and time. The more precisely you know the energy of a quantum state, the less precisely you can know when that energy was measured or how long the state existed. Dex dt garts as 2. This energy-time uncertainty has extraordinary consequences. It means that for brief moments, the universe can borrow energy from nothing, as long as it pays it back quickly enough. The shorter the time interval, the more energy can fluctuate. This leads to one of the most bizarre predictions of quantum mechanics. The vacuum, empty space itself, is not actually empty. At every point in space, at every moment in time, particle-antiparticle pairs are popping into existence out of pure vacuum, existing for a fleeting instant before annihilating back into nothingness. These are called virtual particles, and they exist solely because of Heisenberg's uncertainty principle. You might think this is just theoretical speculation, something we can't observe. But in 1948, Dutch physicist Hendrik Casimir predicted a testable consequence of these vacuum fluctuations. He calculated that if you place two uncharged metal plates very close together in a vacuum, the virtual particles between the plates should create a measurable force pushing the plates together. This seemed absurd. How could empty space exert a force? But here's the logic. Virtual particles of all wavelengths pop in and out of existence throughout space. Between two closely spaced plates, only virtual particles with wavelengths small enough to fit between the plates can exist. Outside the plates, virtual particles of all wavelengths exist. This creates a pressure difference. There's literally more quantum vacuum outside the plates than inside, and this pressure pushes the plates together. In 1997, Stephen Lamoureux at Los Alamos measured the Casimir effect with incredible precision. He brought two gold-plated surfaces to within a few micrometers of each other and measured the force. The results match Casimir's predictions to within 5%. Empty space genuinely exerts a force because of quantum vacuum fluctuations. The uncertainty principle makes nothingness impossible. Let me emphasize how radical this is. Classical physics says that a vacuum is nothing, the absence of everything. But quantum mechanics says that's impossible. The uncertainty principle forbids perfect emptiness. At every point in space, energy and particles are constantly fluctuating into and out of existence. The vacuum is a seething foam of quantum activity. This has cosmic implications. Stephen Hawking realized in 1974 that these quantum vacuum fluctuations near a black hole's event horizon can create real particles. Normally, virtual particle pairs appear and annihilate almost instantly. But near an event horizon, one particle of the pair can fall into the black hole while the other escapes. The escaping particle becomes real, and to an outside observer, it looks like the black hole is emitting radiation. This is Hawking radiation, and it means black holes aren't perfectly black. They glow with quantum radiation, very faintly, and over unimaginably long timescales, they evaporate completely. A solar mass black hole would take 10^67 years to evaporate, far longer than the current age of the universe. But tiny black holes, if they exist, would evaporate much faster. And all of this happens because of Heisenberg's uncertainty principle. The uncertainty principle also explains why atoms are stable. In classical physics, electrons orbiting a nucleus should radiate energy continuously and spiral into the nucleus in a fraction of a second. Every atom should collapse instantly. Obviously, they don't. Here's why. If an electron got too close to the nucleus, its position would become very precisely defined. By the uncertainty principle, that would mean its momentum becomes highly uncertain. High uncertainty in momentum means high kinetic energy, which would cause the electron to fly away from the nucleus. There's a balance point where the electron's quantum nature, its wave-like spread in space, keeps it at a stable distance from the nucleus. Your body, every solid object around you, exists in a stable form only because of the uncertainty principle. Without it, matter as we know it couldn't exist. Now, here's where people often go wrong with the uncertainty principle. They hear that observation affects reality and conclude that consciousness is somehow special, that the mind creates reality. Let me be very clear. That's not what the uncertainty principle says. The uncertainty principle isn't about the act of observation introducing uncertainty. It's about the quantum state itself being inherently uncertain. Before any measurement, before any observation, the particle genuinely doesn't have simultaneous definite values for position and momentum. These properties don't exist with precision until measured, and measuring one necessarily makes the other less defined. This isn't observer-dependent in the sense of requiring a conscious observer. It's observer-dependent in the sense that quantum properties are relational, defined through interaction, not intrinsic. An electron interacting with a detector, with a photon, with any other quantum system, all of these interactions involve the same uncertainty principle. Consciousness has nothing special to do with it. But here's what does blow my mind. The uncertainty principle means that reality, at its most fundamental level, is fuzzy. There is no perfectly sharp, perfectly defined state of affairs. Every quantum system exists in a state of inherent blur, where conjugate properties like position and momentum, or energy and time, cannot simultaneously have definite values. This is profoundly different from classical physics, where everything has a definite state at every moment. In classical physics, if you knew the exact position and momentum of every particle in the universe, you could, in principle, predict the future with perfect accuracy. This is Laplace's demon, the idea that the universe is deterministic, a clockwork mechanism where the future is already written in the present. The uncertainty principle destroys this deterministic vision. You cannot know the exact position and momentum of even a single particle, not because of technological limitations, but because these exact values don't exist simultaneously. The universe is fundamentally indeterminate. In 2012, physicists at the Vienna University of Technology performed an experiment that directly tested the uncertainty principle in a new way. They measured pairs of properties simultaneously for individual photons and showed that the uncertainty relation holds exactly as Heisenberg predicted, even when using measurement techniques that minimize disturbance. The principle is absolutely fundamental. Let me share something personal. When I first understood that the uncertainty principle isn't about our ignorance, but about reality itself being indefinite, it changed how I think about certainty in general. We crave certainty. We want to know exactly where we stand, exactly where we're going. We want definite answers. But the universe, at its foundation, doesn't work that way. Reality is inherently probabilistic, fundamentally uncertain, and maybe, just maybe, our psychological craving for absolute certainty is fighting against the nature of existence itself. I'm not saying you should embrace chaos or give up on planning, but perhaps there's wisdom in recognizing that uncertainty isn't a bug in the system. It's a feature. It's how reality actually works at the deepest level we've been able to probe. Here's a question for you. What would change in your life if you truly accepted that certainty is an illusion, that even the universe itself operates on probabilities rather than certainties? Would that make you more anxious, or would it paradoxically make you more free? The uncertainty principle also has technological implications. Quantum cryptography, which we mentioned briefly earlier, relies on the uncertainty principle to guarantee security. If someone tries to measure the quantum state of a photon carrying encrypted information, the act of measurement will disturb the state in a detectable way. The uncertainty principle makes perfect eavesdropping impossible, but there's a darker side too. The same uncertainty that makes eavesdropping impossible also sets limits on measurement and computation. There are fundamental limits imposed by the uncertainty principle on how precisely we can measure certain combinations of properties. These limits can never be overcome, no matter how advanced our technology becomes. We live in a universe with built-in limitations, not practical limitations, but fundamental ones. Some questions simply don't have perfectly precise answers, not because we're not clever enough to measure them, but because reality itself doesn't have those answers to give. And yet, despite this fundamental fuzziness, the universe manages to produce stable atoms, stars that shine for billions of years, galaxies with intricate structures, and ultimately conscious beings capable of contemplating the uncertainty principle itself. Order emerges from quantum uncertainty. Structure arises from fundamental fuzziness. How? That's a question we're still trying to fully answer. But part of the answer lies in another quantum phenomenon we need to explore: decoherence. Because while quantum systems exist in uncertain superpositions, constantly fluctuating according to the uncertainty principle, somehow, the world we experience appears classical, definite, certain. The uncertainty principle tells us the quantum world is fundamentally fuzzy, but the world we see isn't fuzzy at all. Your chair is in a definite location. The moon is definitely there when you're not looking at it. Cats are either alive or dead, not some fuzzy superposition of both. So, what happens at the boundary between the quantum and the classical? How does definite reality emerge from fundamental uncertainty? That's the question of quantum decoherence, and it's where we're going to turn our attention. Because understanding decoherence is the key to understanding why Schrödinger's cat is never actually in superposition, and why the quantum weirdness we've been exploring doesn't show up in everyday life, even though it's happening all around us at the smallest scales. Here's a puzzle that's haunted physicists for nearly a century. At the quantum level, an electron can be in two places at once. A photon can be both a wave and a particle. Atoms exist in superpositions of multiple states simultaneously. Yet, when you look around, nothing is in superposition. Your coffee cup is in one definite place. Your cat is either alive or dead, not both. So, where does quantum weirdness end and classical reality begin? Is there a magic boundary where superposition collapses into definiteness? In 1970, a German physicist named Dieter Zeh proposed something revolutionary. There is no boundary. Quantum mechanics never stops applying. The reason you don't see cats in superposition has nothing to do with consciousness or observation. It has everything to do with a phenomenon called decoherence, and understanding it might be the key to understanding why reality appears the way it does. If that just made you question everything about the solid world around you, perfect. That's exactly where we need to be. Smash that like button, because we're about to solve one of the deepest mysteries in quantum mechanics. Stay subscribed because decoherence is the bridge between the bizarre quantum world and the seemingly normal classical world you experience every day. Let's go back to 1957. Hugh Everett III, a graduate student at Princeton, was deeply bothered by the measurement problem in quantum mechanics. We've talked about how quantum systems exist in superpositions until measured. But what exactly counts as a measurement? When does the wave function collapse? Does it require a conscious observer? Niels Bohr's Copenhagen interpretation said that measurement causes wave function collapse, but it never precisely defined what measurement means. This led to all sorts of philosophical problems. Does the universe need conscious observers to become real? Did the universe not have definite properties before life evolved? These questions seemed absurd, but the Copenhagen interpretation didn't have clear answers. Everett proposed something radical. What if the wave function never collapses? What if quantum mechanics is perfectly valid at all scales, and apparent collapse is just an illusion created by how we interact with quantum systems? His solution was the many worlds interpretation. When you measure a quantum system in superposition, Everett said, the universe splits into multiple branches. In one branch, you measure spin up. In another branch, you measure spin down. Both outcomes happen, just in different universes. There's no collapse. The wave function of the entire universe evolves smoothly according to Schrödinger's equation forever. This interpretation solved the measurement problem, but it came at an extraordinary price. You have to accept that every quantum measurement creates new parallel universes, that there are countless versions of you experiencing every possible outcome of every quantum event. Most physicists found this too extravagant to accept, but Everett had identified something crucial. If quantum mechanics is universally valid, then there should be no special role for observers or consciousness. The weirdness of quantum mechanics should apply to everything, including measuring devices, cats, and humans. The question is, why don't we see macroscopic superpositions? Then, in 1970, Dieter Zeh, and independently Hans-Dieter Zeh, published a paper that transformed how we think about this problem. He introduced the concept of decoherence, and it provided a completely different answer to the measurement problem. Zeh's insight was this: in real experiments, quantum systems are never truly isolated. They constantly interact with their environment, photons bouncing off them, air molecules colliding with them, thermal vibrations coupling to them. Each of these interactions entangles the quantum system with the environment, spreading the quantum information across a huge number of environmental particles. When a quantum system becomes entangled with its environment, something remarkable happens. From the perspective of any single observer who doesn't have access to the full environmental information, the quantum superposition appears to vanish. The interference effects that characterize quantum behavior become impossible to detect. The system appears to have collapsed into a definite state, even though the full quantum description, including the environment, still contains all the original information in a superposition. This is decoherence, It's not actual wave function collapse. The quantum information doesn't disappear, but it gets spread out, diluted across so many environmental degrees of freedom that it becomes inaccessible. For all practical purposes, the superposition is destroyed. And here's the crucial point. Decoherence happens incredibly fast for macroscopic objects. In 1996, Serge Haroche, who would later win the Nobel Prize in 2012, calculated the decoherence time for various objects. For a dust particle in air, decoherence happens in about 10^31 seconds. That's far faster than any conceivable measurement could be made. For larger objects, it's even faster. This is why you never see cats in superposition. It's not because cats are large, it's because cats interact with their environment trillions upon trillions of times per second. Every photon that bounces off the cat, every air molecule that collides with it, every thermal vibration within its body, all of these interactions entangle the cat with the environment. Decoherence destroys any quantum coherence essentially instantaneously. Schrödinger's cat thought experiment was meant to show how absurd quantum mechanics seemed when applied to everyday objects. But decoherence explains why the absurdity never manifests. The cat, the poison vial, the radioactive atom, the entire apparatus is constantly interacting with its environment. Decoherence would destroy any superposition of alive and dead states long before you open the box. The cat is always in a definite state, either alive or dead, not because consciousness collapses wave functions, but because environmental interaction does. In 1996, a team of researchers led by David Wineland at NIST performed an experiment that directly demonstrated decoherence. They prepared a single beryllium ion in a superposition state and carefully controlled its interaction with the environment. They showed that as environmental coupling increased, the quantum interference effects rapidly vanished, exactly as decoherence theory predicted. They could watch in real time as quantum behavior transformed into classical behavior. Then, in 2000, researchers in Paris led by Serge Haroche created mesoscopic Schrödinger cat states, superpositions of electromagnetic field states containing several photons, and watched them decohere. They could precisely control the rate of decoherence by adjusting how much the electromagnetic field interacted with its environment. When isolated, the cat state persisted. When exposed to environmental interactions, it decohered within milliseconds. These experiments prove that decoherence is real, measurable, and completely explains why we don't see macroscopic quantum superpositions in daily life. But here's where it gets philosophically interesting. Decoherence doesn't solve the measurement problem completely. It explains why superpositions appear to collapse, why the world looks classical to us. But it doesn't explain which outcome you experience. It doesn't explain why you see the cat either alive or dead, rather than experiencing some kind of superposition yourself. Some physicists combine decoherence with the many worlds interpretation. They argue that decoherence creates the branching structure of reality. When a quantum measurement happens, the system and the environment become entangled in such a way that different outcomes exist in different branches, and decoherence ensures these branches can never communicate. You see one outcome because you're in one branch, but other versions of you in other branches see different outcomes. Other physicists argue that decoherence, combined with some additional mechanism we don't yet understand, actually does cause wave function collapse. The quantum state really does reduce to a single outcome, and decoherence explains when and how this happens. We don't know which interpretation is correct. What we do know is that decoherence explains the appearance of wave function collapse with exquisite precision, regardless of what's ultimately happening at a deeper level. Let me tell you about an experiment that shows just how powerful decoherence is. In 2010, a team at UC Santa Barbara created a tiny mechanical resonator, a device visible to the naked eye, and cooled it to its quantum ground state. For a brief moment, this macroscopic object, containing trillions of atoms, was in a quantum state. It was the largest object ever placed in a quantum state. But maintaining that quantum state required extraordinary measures. They had to cool the device to nearly absolute zero, operate in a near-perfect vacuum, and shield it from all external vibrations and electromagnetic fields. Despite all these precautions, the quantum state lasted only microseconds before decoherence from residual environmental interactions destroyed it. This experiment shows two things. Quantum mechanics really does apply to large objects, but environmental interaction makes quantum behavior essentially impossible to observe for anything larger than molecules in normal conditions. Decoherence also has profound implications for quantum computing. Quantum computers rely on maintaining quantum superpositions in their qubits to perform calculations. But decoherence is the enemy. Any interaction between qubits in the environment destroys the delicate quantum states and ruins the computation. The entire field of quantum error correction is devoted to fighting decoherence. Engineers build quantum computers in extreme isolation, cooling them to millikelvin temperatures, shielding them from magnetic fields and vibrations, operating them in high vacuum chambers. Even with all these precautions, current quantum computers can maintain quantum states for only a fraction of a second before decoherence destroys them. This is why building large-scale quantum computers is so extraordinarily difficult. It's not just an engineering challenge, it's a battle against decoherence, against the fundamental tendency of quantum systems to become entangled with their environment. But here's something fascinating. Some scientists now think biological systems might actually exploit quantum coherence in ways we never expected. In 2007, researchers discovered that photosynthesis in plants involves quantum coherence. When a photon is absorbed by a chlorophyll molecule, the energy doesn't simply hop from molecule to molecule randomly. It exists in a quantum superposition, simultaneously exploring multiple pathways, finding the most efficient route to the reaction center. This quantum coherence persists for hundreds of femtoseconds, far longer than anyone expected in the warm, wet, noisy environment of a living cell. It seems that biological systems have evolved mechanisms to protect quantum coherence from decoherence, using it to achieve near-perfect efficiency in energy transfer. Similar quantum effects may occur in bird navigation, where some birds apparently use quantum entanglement in light-sensitive proteins in their eyes to detect Earth's magnetic field. And there's speculative but intriguing research suggesting that quantum effects might play a role in enzymatic reactions, in the sense of smell, and possibly even in neural processes. I'm not claiming consciousness is quantum mechanical. The evidence for that is weak at best, but the idea that biological systems completely avoid quantum effects is clearly wrong. Life exists at the boundary between quantum and classical, and evolution may have found ways to exploit quantum coherence while managing decoherence. Let me share a personal reflection. When I first understood decoherence, I felt both disappointed and relieved. Disappointed because it means we'll probably never see truly macroscopic quantum superpositions. You can't put a cat in superposition, not because of some mystical role for consciousness, but because of mundane environmental interactions. But I was also relieved because decoherence shows that quantum mechanics isn't as fragile as it might seem. quantum behavior doesn't require perfect isolation or conscious observers. It's happening all around us, all the time, at microscopic scales. The classical world we experience emerges naturally from quantum mechanics through decoherence. There's no magic boundary, no special role for life or consciousness. Just physics, all the way down. Here's what keeps me awake though. If decoherence explains why the world looks classical to us, but doesn't actually destroy the quantum information, just hides it in the environment, then what does that mean for reality? One interpretation says all those hidden quantum possibilities are still real, existing in parallel branches we can't access. Another interpretation says they're genuinely gone, that decoherence triggers actual collapse. We honestly don't know which is true. What we do know is that you right now are a classical system only because you're constantly interacting with your environment. Every photon that hits your body, every air molecule you collide with, every thermal vibration in your cells, all of these interactions are entangling you with the environment, destroying quantum coherence, making you appear classical. In a sense, your classical identity is maintained by your connection to the world around you. In perfect isolation, at absolute zero, shielded from all interactions, you would become quantum. Your wave function would spread out. You'd exist in superposition. But in the real world, with constant environmental interaction, you're locked into a definite classical state. There's something poetic about that. Your definite identity, your concrete existence, is created and maintained by your relationships with everything around you. Isolation would make you quantum, uncertain, spread out. Connection makes you classical, definite, real. So, what's the ultimate takeaway? Decoherence explains why quantum weirdness doesn't appear at everyday scales. Not because quantum mechanics stops applying, but because environmental interaction destroys observable quantum coherence. The quantum world and the classical world aren't separate realms. Classical reality is what quantum reality looks like when viewed through the lens of decoherence. And here's a question for you. If your classical definite existence is maintained by constant interaction with your environment, what does that say about the nature of identity itself? Are you a separate thing that happens to interact with the world? Or are you a pattern of interactions defined by your relationships rather than existing independently of them? These are deep questions, and quantum mechanics doesn't answer them directly. But it certainly suggests that connection, relationship, and interaction are more fundamental than isolation and independence. We've covered 6 quantum rules so far: superposition, entanglement, wave-particle duality, tunneling, uncertainty, and decoherence. Each has revealed reality to be stranger, more subtle, and more interconnected than our everyday experience suggests. But we need to go even deeper, because everything we've discussed so far treats particles as fundamental objects. Electrons, photons, quarks. We've been talking about them as if they're little things that follow quantum rules. But modern physics says something even more radical. Particles aren't fundamental at all. What we call particles are actually excitations in quantum fields that fill all of space. Reality isn't made of things. It's made of fields, vibrating patterns of energy and information. And understanding quantum field theory is essential to grasping what the universe actually is at its deepest level. What if I told you that electrons don't exist? Not in the way you think they do. You've been imagining tiny particles, little billiard balls of matter whizzing around. But that's not what modern physics says. What we call an electron is actually a ripple, an excitation in an electron field that permeates all of space. Every particle you've ever heard of, photons, quarks, neutrinos, they're all just vibrations in underlying fields. Matter isn't made of things. It's made of patterns and fields of energy. In 1928, Paul Dirac wrote down an equation that predicted something nobody expected: antimatter. His equation revealed that for every particle, there must exist an antiparticle with opposite properties. 4 years later, in 1932, Carl Anderson discovered the positron, the antiparticle of the electron, exactly as Dirac predicted. And this discovery forced physicists to completely reimagine what particles actually are. If that just shattered your mental picture of reality, excellent. You're ready for the deepest level we're going to explore. Hit that like button, because quantum field theory is the most accurate scientific theory ever developed, and it's about to change everything you thought you knew about existence. Stay subscribed, because understanding fields is the key to understanding what the universe actually is. Let's start in 1928. Paul Dirac was trying to create a version of quantum mechanics that was compatible with Einstein's special relativity. Schrödinger's equation worked beautifully for non-relativistic particles, but it broke down when particles moved at speeds approaching light. Dirac wanted an equation that would work at any speed. After months of work, he found it. The Dirac equation was mathematically beautiful and made precise predictions about electron behavior, but it had a disturbing feature. It predicted negative energy solutions. For every positive energy state an electron could occupy, there was a corresponding negative energy state. In classical physics, negative energy is nonsensical. Energy can be zero or positive, but not negative. Dirac wrestled with this problem. If negative energy states exist, why don't all electrons fall into them, radiating infinite energy in the process? The universe should collapse instantly. Dirac proposed a radical solution. What if all the negative energy states are already filled? He imagined an infinite sea of negative energy electrons filling all of space, invisible because they're in their lowest possible state. If you could somehow remove one of these negative energy electrons, it would leave a hole, and that hole would behave like a particle with positive charge and positive energy. It would behave like an anti-electron. Most physicists thought this was bizarre, an infinite sea of invisible electrons filling the universe. But in 1932, Carl Anderson, studying cosmic rays at Caltech, observed a particle track in a cloud chamber that curved the wrong way. It had the same mass as an electron, but opposite charge. He had discovered the positron, the antiparticle of the electron, exactly as Dirac's equation predicted. Dirac won the Nobel Prize in 1933, just 1 year after the positron's discovery. But the deeper implication of his work took longer to understand. Particles and antiparticles aren't really particles at all. They're excitations in quantum fields. The modern understanding emerged in the 1940s and 1950s, developed by physicists like Richard Feynman, Julian Schwinger, and Shinichiro Tominaga. They created quantum field theory, or QFT, which treats particles not as fundamental objects, but as excited states of underlying quantum fields. Here's how it works. Imagine the electron field, a quantum field that exists at every point in space throughout the entire universe. Most of the time, this field is in its ground state, its lowest energy configuration. You can't see or detect the field in this state. It's just there, filling space. But if you add energy to the field at a particular location, you create an excitation, a ripple in the field. That ripple is what we call an electron. It behaves like a particle because the excitation is localized, but fundamentally it's a wave in the field. When the electron moves, what's really happening is the excitation is propagating through the field, like a wave moving through water. And here's the key insight. Antiparticles are just negative energy excitations of the same field. The positron isn't a different kind of thing from the electron. It's the same field, just vibrating in a different mode. Creating an electron-positron pair is like creating a hill and a valley in the field simultaneously. This might sound abstract, but quantum field theory makes predictions of staggering accuracy. The most precisely tested prediction in all of science is the magnetic moment of the electron, a measure of how strongly the electron interacts with magnetic fields. Quantum field theory predicts this value to 12 decimal places, and experimental measurements agree to within the measurement precision. No other scientific theory comes close to this level of accuracy, but quantum field theory is strange in ways that go far beyond regular quantum mechanics. In QFT, particles can appear and disappear. An electron and positron can annihilate each other, converting their mass into photons, pure energy. Two photons with sufficient energy can collide and create an electron-positron pair, converting energy into matter. E equals mc2 isn't just an equation, it's a description of how fields can transform between different excitation modes. Richard Feynman revolutionized how we think about quantum field theory in the late 1940s. He developed a method called the path integral formulation, and it reveals something profound about quantum behavior. In classical physics, a particle travels from point A to point B along a single path, the path of least action. But Feynman showed that in quantum mechanics, a particle doesn't take just one path. It simultaneously takes every possible path between A and B. Paths that go straight, paths that loop around, paths that zigzag wildly, even paths that go backward in time briefly before moving forward again. Each path contributes to the final probability amplitude with a different phase. When you add up all these contributions, the paths close to the classical path reinforce each other constructively, while wildly different paths tend to cancel out destructively. This is why macroscopic objects appear to follow classical paths. The quantum contributions from crazy paths cancel out, leaving only the classical trajectory. But at the quantum level, all those paths are real. An electron going from one point to another genuinely explores every possible trajectory simultaneously. It's not that we don't know which path it took all of them. Feynman diagrams, which he developed to visualize these processes, became the standard tool for calculating quantum field theory predictions. Each diagram represents a different way a quantum process can occur, and you add up all possible diagrams to get the final probability. But here's where quantum field theory gets truly mind-bending. Remember vacuum fluctuations from the uncertainty principle. In quantum field theory, the vacuum isn't just fluctuating energy. It's fluctuating fields creating virtual particles. At every point in space, at every moment, quantum fields are fluctuating. For brief instants, these fluctuations are large enough to create particle-antiparticle pairs that pop into existence and annihilate almost immediately. These virtual particles aren't directly observable. They exist for too short a time to be measured individually, but they have measurable effects. Virtual particles surrounding an electron slightly alter its properties, affecting how it interacts with electromagnetic fields. These tiny corrections, called radiative corrections, have been measured with extraordinary precision. The predictions of quantum field theory, including contributions from virtual particles, match experimental measurements to more decimal places than any other theory in physics. In the 1960s and 1970s, physicists developed the Standard Model of Particle Physics, which describes 3 of the 4 fundamental forces using quantum field theory: the electromagnetic force, the weak nuclear force, and the strong nuclear force are all explained as arising from exchanges of force-carrying particles, which are themselves excitations in quantum fields. Photons are excitations in the electromagnetic field. They mediate the electromagnetic force. When 2 electrons repel each other, What's really happening is they're exchanging virtual photons, excitations in the electromagnetic field that appear briefly and disappear, transferring momentum between the electrons. W and Z bosons are excitations in the weak field, mediating the weak nuclear force responsible for radioactive decay. Gluons are excitations in the strong field, holding quarks together inside protons and neutrons. And then there's the Higgs field. In the 1960s, Peter Higgs and others proposed that empty space is filled with a field, now called the Higgs field, that has a non-zero value even in its ground state. Particles acquire mass by interacting with this field. The more strongly a particle interacts with the Higgs field, the more massive it is. This was a radical idea. Mass isn't an intrinsic property of particles. It's a consequence of how particles interact with the Higgs field filling space. Photons don't interact with the Higgs field at all, so they're massless and travel at light speed. Electrons interact weakly, so they have small mass. W and Z bosons interact strongly, so they're heavy. In 2012, after decades of searching, the Large Hadron Collider at CERN discovered the Higgs boson, an excitation of the Higgs field. This discovery confirmed that space is indeed filled with the Higgs field, that mass is generated through field interactions, and that quantum field theory correctly describes reality at the deepest level we've probed. But quantum field theory has a massive problem, literally. When you try to calculate the energy density of the vacuum, accounting for all the quantum fluctuations of all the fields, you get a prediction that's absurdly wrong. The vacuum should have enormous energy density, about 10^120 times larger than what we observe. This is called the cosmological constant problem, or the vacuum catastrophe, and it's one of the biggest unsolved problems in physics. Every quantum field contributes vacuum energy from its fluctuations. When you add up contributions from all fields at all possible frequencies, the integral diverges, you get infinity. Physicists use mathematical tricks called renormalization to remove these infinities and make finite predictions for observable quantities. Renormalization works brilliantly for calculating particle properties and interaction rates, but for the vacuum energy itself, we don't know how to fix it. The observed energy density of empty space, measured through cosmological observations of dark energy, is incredibly small but non-zero. It's causing the expansion of the universe to accelerate. But quantum field theory predicts this value should be 10^120 times larger. That's not off by a factor of 2 or 10. That's off by 1 followed by 120 zeros. It's the worst prediction in the history of physics. Nobody knows how to solve this problem. It suggests we're missing something fundamental about quantum field theory, about gravity, or about how these fit together. It's a cosmic scale hint that our understanding is incomplete. Let me share something that fundamentally changed how I see reality. Quantum field theory says that what you think of as empty space is actually the ground state of multiple quantum fields, each existing everywhere simultaneously, each capable of being excited to create particles. You're not moving through empty space. You're moving through a plenum of quantum fields in their lowest energy states. And matter is just places where these fields are excited. An electron is a local excitation in the electron field. A photon is a local excitation in the electromagnetic field. You are not made of stuff. You are made of patterns, organized excitations in quantum fields, vibrations that have coherence and structure. From this perspective, solid matter is an illusion in a precise sense. There are no solid objects, only field configurations. The apparent solidity comes from electromagnetic field interactions between the electrons in your hand and the electrons in the table you're touching. Both are excitations in the electron field, and their interactions, mediated by virtual photons in the electromagnetic field, create the sensation of solidity. You are standing waves in quantum fields. Your physical form is a temporary configuration of field excitations that maintains its pattern through constant interaction and energy exchange. When you die, those excitations disperse, the pattern dissolves, but the fields remain. Energy is conserved, the fields are eternal. Only the patterns come and go. Here's a question that haunts me. If particles are excitations and fields exist everywhere, is there a sense in which everything is connected not just through entanglement, but through the underlying unity of the fields themselves? All electrons are excitations of the same electron field. Are they fundamentally separate, or are they more like waves on an ocean, distinct but not separate? Quantum field theory doesn't give a clear answer to this. But it does suggest that the boundaries between objects are less fundamental than they appear. You and I are excitations in the same set of fields, localized in different regions of space, but ultimately vibrations in a unified substrate. The most common mistake people make with quantum field theory is thinking fields are made of something, that they're in some kind of medium, but fields aren't in space. Space might be in fields, or even be made of fields. Modern approaches to quantum gravity suggest that space-time itself might be an emergent phenomenon arising from quantum field interactions. If that's true, then everything we've discussed, particles, waves, forces, even space and time themselves, are all manifestations of quantum fields. Fields aren't the furniture of the universe, they are the universe. We've journeyed through 7 quantum rules now, each revealing reality to be stranger and more subtle than the one before. Superposition showed us that particles exist in multiple states simultaneously. Entanglement revealed non-local connections. Wave-particle duality demonstrated that identity is contextual. Tunneling proved that barriers are probabilistic. Uncertainty told us that reality is fundamentally indeterminate. Decoherence explained why classical reality emerges. And quantum field theory showed us that particles aren't fundamental, only fields are. But we need to pull all of this together. We need to ask, what does this mean? What is the universe, really, at its deepest level? What do these quantum rules tell us about the nature of existence, about consciousness, about your place in the cosmos? We've been building toward this moment, layer by layer, revealing deeper and deeper structures. And it's time to integrate everything we've learned, to look at the quantum mirror and see what it reflects about reality, about possibility, about what it means to exist in a quantum universe. We've traveled deep into the quantum realm together, peeling back layer after layer of reality's structure. We've seen particles exist in multiple places at once, instantaneous connections across vast distances, identities that shift based on observation, barriers that can be tunneled through, fundamental uncertainty woven into existence, the emergence of classical reality from quantum chaos, and finally, the revelation that particles aren't fundamental at all, just vibrations in eternal fields. But here's the question that matters most. So what? What does any of this mean for you right now, sitting here, living your life? Does quantum mechanics have anything to say about consciousness, about meaning, about how you should live? The answer is subtle, surprising, and more profound than you might expect. Because while quantum mechanics doesn't validate mysticism or give you superpowers, it does reveal something extraordinary about the nature of possibility itself. If you've made it this far, you're in rarefied company. Give yourself a moment of appreciation for sticking with ideas that challenged everything you thought you knew. Hit that like button one more time, because we're about to integrate everything into a coherent picture. And stay subscribed, because this conversation about quantum reality and human existence is far from over. Let's start by addressing the elephant in the room. Does quantum mechanics tell us anything about consciousness? This question has spawned countless books, documentaries, and unfortunately, a massive amount of pseudoscience. So, let me be absolutely clear about what we know and what we don't. In 1989, Roger Penrose, one of the world's leading mathematical physicists, proposed that consciousness might be a quantum phenomenon. Working with anesthesiologist Stuart Hameroff, he suggested that microtubules, structural proteins inside neurons, might maintain quantum coherence long enough to influence neural processing. The idea was that quantum computation in microtubules could explain aspects of consciousness that seemed difficult to explain with classical neuroscience. The Penrose-Hameroff theory, called orchestrated objective reduction, or ORCH-OR, is controversial. Most neuroscientists are skeptical because the brain seems too warm and noisy for quantum coherence to persist. We know from decoherence that quantum states are incredibly fragile. The warm, wet environment of a brain should destroy quantum coherence in femtoseconds. However, and this is important, the discovery of quantum effects in photosynthesis and bird navigation has made scientists less certain that quantum coherence is impossible in biological systems. Some recent experiments suggest that microtubules might maintain quantum states longer than expected. The question remains open. But here's what I want to emphasize. Even if consciousness turns out to have quantum aspects, that doesn't mean you can use quantum mechanics to manifest your desires, or that observation creates reality in some mystical sense. Quantum effects in the brain, if they exist, would be about information processing, not about bending the universe to your will. The measurement problem, the question of what causes wave function collapse, is still unsolved. Some interpretations, like the many worlds interpretation, suggest that consciousness plays no special role at all. Other interpretations, like some versions of the Copenhagen interpretation, give consciousness a central place. We honestly don't know. What we can say definitively is that quantum mechanics reveals the universe to be probabilistic rather than deterministic. And that has profound implications for how you think about your life, regardless of whether consciousness is quantum. In a deterministic universe, the kind Einstein believed in, the future is already written. Given the exact state of every particle at one moment, the laws of physics determine every subsequent moment with perfect precision. You have no real choices. Free will is an illusion. You're a puppet of the initial conditions set at the Big Bang, a biological machine executing its predetermined program. But quantum mechanics shatters this picture. The uncertainty principle, the probabilistic nature of quantum measurement, the genuine randomness at the heart of radioactive decay, all of these tell us that the future is not determined by the present. Reality contains irreducible randomness. The wave function gives probabilities, not certainties. Now, quantum randomness by itself doesn't give you free will. Random quantum events in your brain wouldn't make you more free, they just make you more random. But what quantum mechanics does is open space for agency that doesn't exist in a deterministic universe. The future is not written. Possibility is real. Let me share a moment from my own journey with these ideas. When I first understood that the universe is fundamentally probabilistic, I felt simultaneously liberated and terrified. Liberated because it meant the future isn't predetermined, that genuine novelty is possible, that the universe is still creating itself. Terrified because it meant there are no guarantees, no cosmic plan ensuring everything works out, no deterministic laws protecting me from chaos. But over time, I've come to see quantum indeterminacy not as threatening, but as essential to what makes existence meaningful. In a deterministic universe, nothing genuinely matters because everything is predetermined. Your choices are illusions. Your struggles are theater. But in a quantum universe where the future is genuinely open, your choices participate in creating reality. You're not just observing the universe unfold. You're part of how it unfolds. This isn't mysticism. This is taking seriously what quantum mechanics actually tells us, that reality at its foundation is probabilistic, that the wave function of the future contains multiple possibilities, and that interaction, measurement, decoherence, these processes select among possibilities to create actuality. Let's talk about entanglement again, but from a different angle. We discussed how particles that have interacted remain correlated regardless of distance. But think about what this means for your relationships with other people. When you interact meaningfully with someone, particles in your brain and their brain exchange photons create correlations, become briefly entangled before decoherence destroys the quantum coherence. These quantum correlations are destroyed essentially instantly. But the classical correlations they create, the information exchanged, the memories formed, those persist. In a very real sense, every meaningful interaction you have leaves an imprint, not just in your memory, but in the physical structure of your brain and the other person's brain. You become entangled, not quantum mechanically in any lasting sense, but informationally, causally, inevitably. The boundaries between self and other are more permeable than they appear. You are not a closed system. You're an open system, constantly exchanging energy, information, and causality with everything around you. The quantum rules we've explored, superposition, entanglement, decoherence, they all emphasize relationship over isolation, interaction over independence, connection over separation. Wave-particle duality taught us that identity is contextual, that electrons manifest as particles or waves depending on how they're observed. Is there a metaphor here for human identity? Are you fundamentally different in different contexts, with different people in different roles? Or is there some essential you underneath all the manifestations? Quantum mechanics suggests that perhaps identity is more fluid than we usually think, that what manifests depends on context and relationship, and that this fluidity isn't a weakness, but a fundamental feature of how reality operates. Quantum tunneling showed us that barriers are probabilistic rather than absolute, that the impossible and the highly improbable are different categories. This doesn't mean you can tunnel through walls, but it does suggest that obstacles in life might be more permeable than they appear. That probability is different from impossibility. That persistence in the face of low odds can sometimes lead to breakthrough. The sun has been proving this for billions of years. Every second, protons overcome barriers they shouldn't be able to overcome, and life exists because of it. The impossible, repeated enough times, becomes inevitable. The uncertainty principle revealed that reality is fundamentally fuzzy, that perfect knowledge is impossible not because of our limitations, but because of reality's nature. And perhaps there's wisdom in accepting this, in recognizing that the craving for absolute certainty is fighting against how the universe actually works. You cannot know everything. You cannot predict everything. You cannot control everything. And that's okay, because that's how reality is at its deepest level. The universe operates on probability, not certainty. Maybe you should too. Decoherence showed us that the classical world emerges from quantum weirdness through interaction with the environment. Your definite classical existence is maintained by your constant connection with the world around you. Isolation would make you quantum, uncertain, spread out. Connection makes you classical, definite, real. There's something profound here about the importance of relationship, of engagement, of participation in the world. You become real through your interactions. Identity is relational, not isolated. And quantum field theory revealed that you're not made of stuff, but of patterns. organized excitations in quantum fields. You're a standing wave in the electron field, the quark field, vibrating configurations that maintain their structure through constant energy exchange. When you die, the pattern dissolves, but the fields remain. Energy is conserved, the substrate is eternal, only the patterns come and go. This might sound depressing, but I find it strangely comforting. You're not separate from the universe. You're a temporary way the universe has organized itself. You're not in the universe. You are the universe, locally concentrated, temporarily coherent, eventually dispersing back into the field configurations from which you arose. Let me address something important. I've been drawing philosophical implications from quantum mechanics, but I want to be clear. Quantum mechanics doesn't prescribe how you should live. It doesn't tell you what's moral or meaningful, but it does reveal what kind of universe you live in, and that can inform how you navigate existence. You live in a universe that is fundamentally uncertain, deeply interconnected, probabilistic rather than deterministic, and made of patterns rather than stuff. A universe where barriers are negotiable, where identity is contextual, where connection is more fundamental than separation, where the future is genuinely open. What you do with that information is up to you. But for me, understanding quantum mechanics has made me more comfortable with uncertainty, more appreciative of connection, more willing to embrace fluidity, and more in awe of the sheer strangeness of existence itself. Let's return to that night in Brussels in 1927, where we began. Einstein and Bohr walking the streets, arguing about whether God plays dice with the universe. Einstein wanted reality to be deterministic, comprehensible, independent of observation. Bohr embraced the weirdness, the uncertainty, the contextuality of quantum mechanics. Nearly a century later, we know Bohr was right. Reality is exactly as strange as quantum mechanics says it is. Every experiment, every test, every technological application confirms it. The universe really does play dice. Particles really do exist in superposition. Entanglement really is non-local. Wave-particle duality really describes nature. Uncertainty really is fundamental. Quantum fields really are the substrate of existence. And yet, despite being proven wrong, Einstein's resistance to quantum mechanics wasn't entirely misguided. His insistence that there must be a deeper explanation, his discomfort with indeterminacy, his search for underlying order, all of this drove physics forward. Without Einstein's challenges, quantum mechanics might not have been developed as rigorously. Sometimes being wrong in the right way is more valuable than being right passively. Einstein was wrong about quantum mechanics, but his wrongness was productive, generative, essential to the theory's development. There's a lesson here about holding your beliefs lightly, about being willing to be wrong, about recognizing that resistance and questioning can be valuable even when they don't change the ultimate conclusion. Einstein died still believing quantum mechanics was incomplete. He was wrong, but his legacy includes helping to create the very theory he opposed. So, where do we go from here? Quantum mechanics is the most successful scientific theory ever developed, but it's not complete. We still don't fully understand how quantum mechanics and general relativity fit together. We still don't know what dark matter and dark energy are. We still haven't solved the measurement problem or the cosmological constant problem. We still don't know if there are deeper layers beneath quantum fields. Physics continues. The exploration of reality continues. And every answer raises new questions, deeper mysteries, further frontiers to explore. But for now, for you, what matters is this. You live in a quantum universe. A universe stranger and more wonderful than common sense suggests. A universe that is fundamentally uncertain, yet produces stable structures. A universe that is deeply interconnected, yet allows for individual identity. A universe that is made of pure energy configured into patterns, one of which is you. You are quantum patterns in eternal fields, briefly coherent, magnificently complex, ultimately transient. You are the universe experiencing itself, locally concentrated, temporarily aware, inevitably returning to the field configurations from which you arose. And during your brief moment of coherence, during this fleeting pattern's existence, you have the extraordinary privilege of understanding, however imperfectly, what you are and what kind of universe you inhabit. That understanding doesn't make you immortal or give you superpowers, but it does offer perspective, a way of seeing reality that's truer than everyday experience suggests, a glimpse of the quantum foundations supporting classical existence. The 8 quantum rules we've explored, superposition, entanglement, wave-particle duality, tunneling, uncertainty, decoherence, quantum field theory, and their implications for meaning and existence, these aren't just abstract physics. They're descriptions of the universe you actually live in, the reality you're actually made of, the quantum foundations that make your existence possible. And perhaps most importantly, they remind us that reality is far stranger, far more subtle, far more mysterious than we usually appreciate. The universe is under no obligation to make sense to you. It's under no obligation to conform to your intuitions. But if you're willing to let go of those intuitions, to embrace the strangeness, to follow the mathematics and the experiments wherever they lead, you'll discover a reality more fascinating than any fiction. That's what quantum mechanics offers. Not comfort, not certainty, not control, but truth. Hard-won, experimentally verified, mathematically precise truth about the nature of existence at its deepest level. And that truth is weird, gloriously, impossibly, beautifully weird. Thank you for taking this journey with me through the quantum realm. Thank you for wrestling with ideas that resist intuition, for staying curious even when things got strange, for being willing to question everything you thought you knew about reality. We've explored the night reality cracked open in Brussels in 1927, and we've followed the implications all the way down to quantum fields and the nature of existence itself. It's been a long journey, but I hope you found it worthwhile. If these ideas have sparked something in you, if you're seeing reality a little differently now, share this with someone who needs their mind expanded. Leave a comment about which quantum rule affected you most deeply. And stay tuned, because the exploration of reality's deepest mysteries continues. The universe is quantum. You are quantum. And that changes everything. Until our next journey into the heart of existence, keep questioning, keep wondering, and remember, reality is always stranger than you think, and that's exactly what makes it so magnificent. Sweet dreams, fellow travelers in the quantum realm. May your wave functions remain coherent just long enough to experience the extraordinary mystery of being alive in this impossible, improbable, utterly quantum universe.